Hello and welcome everyone. This is chapter 18 of the Crystal Clear Electronics video series. In this chapter, we'll cover the USB connection divided into 4 separate videos. The curriculum was written by Gábor Kalmár. Today we have Szabolcs Veréb as our lead speaker. He is an assistant lecturer at the Budapest University of Technology. Szabolcs, would you mind telling us a bit about yourself and your work?
Hi there. Well, I'll try. I work with power electronics, that is, electronic devices that do power conversion. I haven't said much more about it, but some examples are chargers for electric cars and inverters that control electric motors. It's quite a wide field. I recommend it, especially for electrical engineers. Let me introduce you too. In today's video, Dávid will assist me in presenting this chapter of the curriculum.
Thank you for the introduction. I am a graduate student of Bolyai High School in Szombathely. When applying to university, I chose the electrical engineering course of BME as my first place of choice, mainly because of the various electronics-related study courses. Before we get started, could you please briefly summarize the practical significance of USB connection and why it is so widespread nowadays?
USB stands for Universal Serial Bus, and it is the most common interface on computers today. It was created to unify the way peripherals were connected to a computer and to replace outdated standards. Today, a very large percentage of peripherals are connected through USB, such as keyboards, mice, printers, phones, and so on.
In this video series, we want you to be able to control our microcontroller from a computer via USB. As our microcontroller doesn't have a built-in USB peripheral, we can't directly connect the signals in the USB connector to its pins. Instead, there's an interface for serial communication, which is the UART. With this peripheral, it is possible to connect to a serial COM port of the PC. The problem is that on modern PCs and laptops, these serial ports are very rare, but almost all of them have USB. The PC side USB and the microcontroller side UART is connected by a special integrated circuit called the FTDI FT232R USB UART converter. With this solution, it's almost like communicating with a real serial port because the PC software emulates the behavior of a serial port over USB, hiding the USB implementation from our eyes. We don't even have to think about it. The UART acronym stands for Universal Asynchronous Receiver Transmitter. Asynchronous communication means that the sender and the receiver are not synchronized. There is no common clock signal, which would determine the timing of the communication. Communication happens over 2 signal lines. One is the RX, or receive, and the other is TX, meaning transmit. These 2 lines are called a data bus, or simply bus. When we talk about bus status later, it will mean the voltage levels of these 2 signal lines. Voltage can be measured only relative to something. In this case, voltage level means the potential difference between the ground and the signal line. Both signal lines can transmit and receive data. RX and TX only mean something in the context of a chip, because the TX line of one device is the RX line of the other device. This also means that we connect 2 UART-compatible devices by connecting the RX pin of a device to the TX pin of the other one, and vice versa. Because the communication is asynchronous, the receiver must know when the transmitter starts transmission and when it ends. The standard describes special states for beginning and ending a transmission. A given package of data between the starting and ending bus states is called a frame. The data frame consists not only of the data, but the start bit, which is used for synchronization, the stop bit, and an optional parity bit. The structure of the frame can be seen in this figure. The bus is logic high in the default state.
the first bit is always a logic 0, called the start bit. This is followed by 5 to 9 data bits. Most often, 8 bits are used, since that is exactly 1 byte. After that, we can optionally use a parity bit. The meaning of this will be discussed in more detail in a minute. Finally, the end of the frame is indicated by logic level 1 for the duration of 1 or 2 bits. For correct operation, both the transmitter and the receiver have to interpret the bits on the bus the same way, or in other words, agree on the same frame structure, and the speed of the communication is called the baud rate. The latter is necessary, so the receiver samples a bit at the same time that the transmitter actually transmits it. The most common format uses 1 start bit, 8 data bits, and 1 stop bit without a parity bit.
I think the meaning of the parity bit needs a little bit explanation. I'm not sure if you've come across the term before.
In any 8-bit binary number, the number of 1 digits is between 0 and 8. An even parity means that for every byte where the number of 1 digits is even, that is 0, 2, 4, 6 or 8, the parity bit stays 0, while if the number of 1 digits is odd, the parity bit becomes 1. Generally, in case of an even parity, the parity bit will be such so that the combined number of 1 digits in the data bits and the parity bit will be even. When using an odd parity, the reverse is true, so the parity bit will become 1 to make the combined number of 1 digits in the data bits and the parity bit odd. Suppose that the received data is 011000101. The even parity of this message is 0 because there are 4 digits of 1, and the odd parity is 1 because 4 is not an odd number. The parity bit is used for error detection. The bit is generated on both the transmitter and receiver side, and if the receiver gets a different result compared to what is included in the message, it signals a received error. With this method, we can detect a fault where an odd number of bits are received incorrectly. If you think about what happens if 2 bits get flipped during a transmission error, you can easily see that the parity will remain the same, so the error goes undetected. If a third bit is also flipped, the error appears again. Typically, parity bits are designed to detect single-bit errors. There are ways, of course, to detect other errors with greater reliability, but that is not the job of the UART physical layer.
The receiver and transmitter must agree not only on the format of the frame, but also on the speed of communication.
In digital communications, the term baud rate is commonly used to describe the data rate. Its unit of measurement is symbols per second. A symbol can have more than just 2 states, so it can carry more information than a single bit. For example, the letters of the alphabet can be symbols. In the English alphabet, there are 26 letters, so in this case the symbol can take 26 states. To count to 26 in binary, in other words, to encode a letter, you need at least 5 bits. In this case, 1 baud per sec equals 5 bits per sec. In UART communication, symbols are bits, so the baud rate and the bit rate are the same. 1 baud per sec equals 1 bit per sec. Baud rates have standard values in UART communication, starting from 2400 bits per second up to 1 megabit per second if the devices are fast enough. A few usual values are 4800, 9600, 14400, 19200. You can see that the values are approximately 1.5 to 2 times bigger than the previous ones. A full list with all the supported values can be found in the relevant chapter of the ATmega16A datasheet.
I suppose we have all the necessary theoretical knowledge to try USB communication with our microcontroller in practice. In the following video, we will show you the interface circuit between the computer and the microcontroller and explain the setting required on the computer.
Bye!